Okay, so we've got, we're going to finish up on fluids in this reading. Things that I want you to focus on, right? So we're going to deal with what we call incompressible fluids, right? Where the density remains constant. We're largely going to deal with what we call laminar fluids, steady flow, okay? So keep that in mind. And the other thing we're going to do is we're not really going to spend time with viscous fluids, but I'll come back to that in a second. So really, what does all this mean, right? So we have a lot of pieces here that give us a model. Okay, so your focus here in the reading is to try to get beyond the jargon, right? If you want to make a table of terms that you can turn to, that might be helpful. In this section, we sort of put a lot of pieces together. We dealt with fluid statics mostly in the previous class, and now we're dealing with fluid dynamics. When we put the pieces together, one, you're going to see the continuity equation. It's a fancy word for mass is conserved, right? So imagine a tube, right? So liquid fluid moves through the tube, and if I change the area, the cross-sectional area of the tube, well, the amount of mass that I send through there can't change. That's what the continuity equation tells us, right? The other thing that we learned from the Bernoulli equation is that if I increase the velocity of the fluid, I lower the pressure. So when you look at the term in the Bernoulli equation that has the speed in it, 1/2 density speed squared, 1/2 rho v squared, think about it that way, right? That as I increase the velocity, the pressure goes down, pressure of the fluid. Okay? The final piece here is that fluids that are at a lower height have a larger pressure. Okay, so this is the idea that we talked about before, that as I increase depth, the pressure goes up. Well, the same thing is true for Bernoulli's equation, but it's just a conservation law. So if you want to work through the derivation in the text, great. I'm not going to. But the derivation in the text of Bernoulli's equation is just the work energy theorem. Okay, I'm not going to spend time in class, but if you find that helpful, absolutely use that. I think that example 13.12 is a really great one, so do that one, right? Push yourself to try to understand it. The stop to think problem, 13.5, is also useful. Make sure that you can do those. Finally, I'm not going to spend much time on section 12.7. That deals with viscous effects. So now we incorporate the fact that the fluid sticks to each other, right? It resists shearing. That's what we call viscosity. You have a problem on it, but honestly, I don't care so much about it. It's it's a slight complication on this model that we're dealing with. So do the problem, but I'm not going to focus on it. It's not going to be a focus on this class or on the exam. So basically, you're going to learn a little bit to do that one problem. Again, it's model building, so we're adding complexity to the model, but we're not doing much more than that. Okay? There's a lot of rich physics in fluid dynamics. Spend some time with it. Try to develop your intuition for it. It can be kind of tricky because you have to bridge that intuition and the math. Make sure that you come and talk with me. We're going to do a longer form example in class, but nevertheless, always make sure that you come and ask questions as they come.